And we are going to continue along the same topic, but a little bit more network focused this time. And I would like to welcome Peter Lundqvist from Arista to give the next talk.
Wow. I think I was here 2020, and it's probably the size of that square there. So applause to you guys. Second one, I heard that, your neighbor doesn't really be the nuclear expert. Apparently he is. Imagine doing here and speaking and knowing that 50% or more knows by far more than you, right? So if you feel pity of yourself, you sit there, just stand in my shoes, right? All right. AI. It was not very encouraging this morning. I had breakfast. I think it's 2 tables away. Oh no, there are going to be 2 sessions about AI. So that's where we are. But, I'm going to try to be very techy as possible because building AI fabric, that's sort of what we are doing. The train has left the building. AI bubble, yeah, of course. I mean, we have seen one of them. There will be more. But I bet that junior people now, they're using chatbots by far more than Google. That's a fact. And you have to be brutal honest. Chatbots are by far better if you know what to look for. So I in that topic, that's unstoppable. Most of you here have learned how to master TCP, SAC fields, and retransmission. You just have to learn about AI workflow. That's it. Suck it in. And how many in here are Danish people? Well, I like to see an American from Texas doing serious patrol in Greenland, really. I like to see that. No, that would not happen. All right. A few buzzwords. Most of you people, how many people here have been gamers? Raise a hand. So you know inside out about the GPUs, right? So I'm not going to go into that. Collective communication, that's what I deal with. Actually, the networking part for collective communication, I will come to that. There's a whole range of buzzwords that you can sit on dinners and fledge out. Not just LLM, there's barrier, gradients, descent, all that. I will briefly touch into it because I like to talk about the networking piece. So I'm not going to talk that much about the algebra because this is algebra, like it or not. CPU and GPU. I showed this slide to my wife. I tried to explain the difference between a CPU and a GPU when I told CPU, complex task one at a time. GPU, parallel task at the same time. So it's very much an analogy to a man and a woman, right? You can also say that my very stupid comment, right? Yep, it's very true, honey, because GPU is by far more expensive than a CPU. So that's a fact. The whole thing with the AI or AI bubble is that there are 2 things of networking with AI. There is single GPU and there's multi-GPU. And all these big data centers there is utilizing the multi-GPU factor. That means that you have a lot of these GPUs and you're working in parallel tasks. Because there are mathematical theorem that says that if you have a data set, chop it into paths, divide it, and then pull everything together at the end, it will be equally good as one unit solve the whole data set. So that is the AI workload in a nutshell, parallelism. Collective communication. If you're going to be in a networking part with anything with AI, these are the stuff that you will be aware of, because these are the ones that sort of steers how the workflows are. They are divided into 3 stages. It's the data movement. That is how the data comes to each GPUs. It's the aggregation. That is how you share the result between GPUs. And there's a synchronization when you bring everything together and you sort of you have solved the project or the training. These are the 3 stages of any AI run. There's not a 4th or a 5th or a 6th stage. These are the stages. So if you're talking to this mad scientist and being a networking guy that I am, these are the things that I need to figure out. Is it all reduced? Or is it broadcast? Because then I know what the traffic pattern will be. So this is our training look like. You have a data set, which is sort of thinking there was a problem or a self-driving car or whatever. I mean, there's a whole bunch of data there. Right? You chop that into pieces, divide it out to each GPUs. That's the propagation part. Then you have a mathematical term, which means that you're running a forward and backward pass, and that is all maths. And you're going to come to what's called a descent, which means that now you sort of have come as close to possible where the truth are, and then you share that with all other units, and then you start all over again. This is how, in a graphical theorem, how an AI run look like. And if you don't trust me, you know, chat GPT it, and you see if you get a different answer. How many here deals with data center? Please raise a hand. How many here are internet jockeys and do an operator? Raise a hand. Oh my God, I had to put the wrong t-shirt on then. All right. So most of the experience with the AI workload is based from data center, but I will come to later part how that is actually moving outside the data centers. But the data centers for these AI fabric, they look fairly the same. It's IP-based. There is no layer 2 clusters in any kind here, or trunk ports, or any other madness. It's IP. Second thing is that everything here is load balancing. And load balancing here is not just for the performance, but also for the convergence, because the best convergence is the one that's always in use. And the third part, it's BGP. I have a few customers that runs with link state, but they are minority. It's BGP. So if you have a solid BGP knowledge, then you can, you know, build AI data center, because the rest are just mad scientists. How does a DGPU look like? Well, here comes the sort of the ultimate power, right? So it's essentially divided based on where to get the data. So there is what's first of all called the front end. The front end is what's called the CPU port. So that is how these servers can grab the data. That comes from storage. These are the CPU ports. And then you have the GPU ports, and that's the interaction between GPUs, and they runs in something called backend. So if you look at this beast here, it has 8 times 400 gig just for GPU to GPU communication. And then you can add 2 to 4 whatever CPU communication. That is just to get the data set into each GPU. Because remember, each GPU has its own memory space. So this is like a microcomputer within a computer. There are some slight variation, but the ones that have worked with NVIDIA can see this is a H100, which is sort of stands for majority today of these big data centers. Deep seek or not. That's how they look like. Fabrics can be small or big. Not everything is in Memphis with 100 to 200,000 GPUs. Actually, most of them are actually single GPU fashion. And that is less of a problem in regards to networking. If you put all these GPU into one switch, you will have not so much to worry about. But this is like exactly when you meet a girl, get married, get kids, get dogs, summer place, all that stuff. That's exactly the same thing. When you start with AI, it will become to a fabric. And that's when the sort of the challenge starts, because that is not the easy approach. So how does it look like? Well, you have something called the front end and back end. People that have been dealing with storage, this is no news. The front end is very much similar to a normal data center. That's where you put all your storage and so forth. You can have over provisioning here. That means that, for instance, you can have 3 times more access ports than trunk ports. So there is a slight bit of over provision allowed here, because usually you run TCP over NFS or CIFS between the storage and the service in question. Not with the backend. There's no over provision whatsoever. So if you have 400 gig in dense to the GPUs, you need to have 400 gig or 800 gig dense on your spine ports. There's no room here for any form of drop packets. So that explains sort of the complexity and also the cost of these data centers. Are there alternative topologies? Yeah, if there will be an NVIDIA guy, he will talk in tongue for the lower one. The upper one is from ICOM, I see it as a, do routing, and then you don't need to care because then your GPUs, whoever GPU can talk to each other because it will be a routed decision to find the destination. The lower one is very much like ATM PVCs for those that are very old like me. You essentially pull up everything. That means that GPU zeros, they all terminate on the same switch, and then it's just physical patching. I would say that the truth of building these is something in between, because usually using both at the same time. Because the problem here with the lower one that might think to be easy one is that it take a hell of a time to build, because obviously you patch the wrong cable to the wrong GPU, or the fact that there's a lot more fibers here and fibers can break. So the truth here is something in between about the topology in question here. I have seen them both and I build both. Now it comes to the traffic. There's something called RDMA. So with the traffic between an AI, you try to avoid to have the Linux kernel involved. So that means that a memory space from each GPU talks to a memory space on another GPU. And that is called RDMA. So that's just one more of these funky words. So if you name that on a party and there's an AI guy there, you will be the most popular guy. In that memory then is divided into something called queue pairs. And queue pairs is segment of the memory that contains the data sets. So I will come to that. That's a very important piece for the networking part. No one really using layer 2. Yeah, I mean, InfiniBand had their show. It's over. Everything is in IP now. So Rogue Vision 2, what it takes is the previous RDMA header and just stack an IP UDP header to it. That's it. No more advanced thing than that. Just adding an IP and UDP header to it. And then you have now a routed packet, right? So this packet now can you put into an IP fabric. What are the challenges with this? Well, first of all, there's not much of entropy. These are what in old terms called elephant flows. There's a destination GPU where the queue pairs are. There's UDP source port. Well, not really. There is a UDP destination port. Well, all the same. So doing 5-tuple load balancing here will not help you that much, right? Because you will not be able to distinguish jobs between two GPUs if you're doing the 5-tuple load balancing. So that's one other thing. The other thing here is you can't drop this packet. So anyone here has spent years of career building class-based VRQ, deficit round robin, priority queuing, or whatever, don't waste your time. Because the trick here is not to drop packets. So you need to come up with a thing called pacing them, not dropping packets. That's the name of the game for all these AI parts. Again, having buffers is good, absolutely. But divide them into queuing, pretty pointless. Much more important that the hardware that you have has the capability to see that there are bursts now going on or there are delay. Because that with telemetry then can indicate that you have a wrong design, which GPUs that talk to each other. This is by far more important than doing any QS designs. I'm monitoring, by the way, all of you here. So all of you that sits, I will be on the social event tonight and have a good memory. So one of these tricks here, I have spent most of my career actually disabling pulse frame. These annoying things that happen because a server is busy and it signals to the networks to shape down and someone complains that I don't have line rate, right? So most of my career I have disabled this stuff. But this is very much in common. The only thing that you can have, for instance, if you have a spline, that is that you connect everything to one device. So the trick here is that if you're about to saturate a link, you signal with a pulse frame where the traffic comes from to please shape down. And you signal it with a timer. So the first packet here says shape down, and it is a timer there. And the second packet sends the same timer suddenly to 0. That means, okay, release the flood. So you will see there's a lot of pulse frame going back and forward. The trick here is to lower the rate because you cannot drop packets, right? You can handle temporary burst, but there's no QoS here between AI flows. There's no lesser important queue pairs than anything else. So pulse frame in an old style, that is the priority flow control. The problem with that is that it's not routed, right? That's a layer 2 solution. So you can actually do it in sequence on all links to the network, but that means that you propagate on one link. So it will be very slow to the ones that you want to shape down, which is actually the server. So there's who knows about the deserve code point in here? Please raise a hand. You are all liars. Who knows about IP precedence bits here? Raise a hand. So you have, is a whole audience not done any QoS in network? Are you voting for Trump? All right. So there is those 2 bits that I spent my career earlier when I was working with operators to figure out what the hell have we prioritized 2 bits for? And that's the XLP congestion bits. The whole idea here is to be able to have some bits that you can signal to the source directly and sort of speed up. So with TCP, it works like this, that suddenly in the network you have a congestion. The bits are set, you have a congestion for this particular session. And on the receiver side, okay, I have congestion. It sets the bit in the acknowledged packet for TCP to the source, and the source will then lower the congestion window. And the congestion window number of packets you send before waiting for an ACK, right? This has been rolling around for TCP-based storage for some time, and works tremendously good, and works by far faster than waiting for 3 duplicate ACKs or a timer or something like that. It's just one problem. What is the problem? Other than that, I see AI fatigue already here. That is that RDMA is over UDP. So within the protocol of RDMA, it actually is a packet type that can signal back. So it's the same configuration you can do with the DSO code point bits, but in the acknowledgement packet back is essentially an RDM packet that says, please lower the speed. So it works exactly the same as TCP. So this is actually a well-used function to throttle down if you, for any kind, has not succeeded in your design, which GPU that talks to which GPU, because you haven't figured out if this is all reduced or broadcast or whatever style. So this is a very good tool to use. Where should I point it so it... this direction. So that is... Oh, hi. You're more or less good looking, by the way. Another thing to solve here, let's see where I am. It's the load balancing part here. So I did tell you there's not much of 5 tuple here, right? So, but what you need to do here is to read into the packet. So anyone that has done MPLS networking, then you most often are forced to read into beyond the MPLS header to get proper load balancing. Here's the same thing. So with the InfiniBand, you read 40 bytes into the packet, then this queue pairs discovered. Then at least you can load balancing different flows from the same GPU. This is the only way to do it. But this is very, very trivial load balancing. And it's gonna actually, you're gonna commute to some part, but it's not gonna be the ideal solution. But most vendors have this implementation. And if they don't have it, well, they have never seen AI. So it's no question of that. So you need to be able to read RDMA in order to proper load balancing. Another thing is do cluster load balancing, and that is you still run RDMA or dynamic load balancing. However, you do snapshot of packets going out to the CPU, where you also try to figure out write codes. And write codes, if you start from queue pairs a new data set, right? And that one you can load balancing. So more and more very advanced features needs to be created if you build the fabric. That's the story behind it. Right. Then suddenly the 28th of January arrived. These are two curves. By the way, they are not after Trump's latest announcement. They are set from 28. And one is NVIDIA and one is the, 10 minutes. Then one is the conference. So, I mean, we were very humble after that, right? And one thing is that, AI and these type of jobs definitely will happen. But do everyone have afford with this? Or will there be this bubble just because it's so costly? So, can you run AI jobs? Can you build a plane or a new market machine for rent from if you're from bank or something else with AI? Absolutely you can. Can you rent that capacity somewhere? Yeah, I mean, that's the second phase of this AI evolution. That's the hosters of AI. They essentially build an AI network and then you can rent it. Chat, can you run it on the cloud? Yeah, absolutely. I mean, all these chatbots is an example of it, right? But if you are a company and you need some time in running AI, let's say for 1 or 2 weeks, yeah, that's the next avalanche of services, right? Call it AI as a service or whatever. With that comes some challenges. Without data, this is pretty useless. So you need to move that data to this site where you have it with all these restrictions. You need to be virtual SAN, you need to be protected from another virtual entity and so forth. The next thing is that you need to divide the GPUs into VRF and all that stuff. But all of you that has built EVPN and that type of data centers, you will find this is not, I like to say rocket science, but these days not even rocket science feels good to say, right? So I guess brain surgery is something that I have to say, because by far he can't be a brain surgery. All right, running workloads outside the data center. To begin with, I don't know any operator that can guarantee 400 gig end-to-end without any loss or reorder. I find that very unlikely. Second topic there is that all this mechanism that I talked about, if you encapsulate that in a VXLAN or MPLS header, I mean, the packet will be encapsulated, right? So in that network, you cannot, achieve any sort of back pressure mechanism. Every time I'm supposed to talk about network, there's someone that asks me about SRv6. All I can say, I don't really see how SRv6 can do the job particularly better than MPLS here. Maybe with the flow label, I don't know. But I just parked that session. So if anyone Cisco wannabe, I will be on the social. We can bore ourselves out and have a talk about that. Are operator cores dumb? No, they have evolved to very advanced things. You can run it with a protocol called TWAMP. That means on each link you can figure out the delay and that it exported in ISIS, TLV, and then you can do your traffic engineering. But the problem here is that these are spoiled childs, right? So the most important one is the gradient sync time here. And there's a difference here, if you can see it on the fourth one, of 30 milliseconds from the average of 120. And if you would see an AI team seeing this difference, they will go haywire. That's not acceptable, because then you can run out of synchronization. So this is really, really complicated to run these AI flows as you do it in a data center. Can we do something else? Lower the speed. Yeah, you can always lower the speed, but that probably takes the whole parallelism out of it. Can you add longer synchronization time? That means that you spend more time to figure out that the data now is collectively having the same result. Yeah, but that is already done today. Can you move to other protocol? Lot of work is now looking into the QUIC. The QUIC is a UDP, but with a congestion mechanism. So that is probably a safe bet that RDMA will run over QUIC in a very short amount of time. Single GPU design. Well, I think most of the designs that where GPUs going to talk to each other most probably will not happen. Instead, there will be single GPUs here and there, and they will, in one way or another, interact with each other because they share the same storage. All right, last slide. This is no brain surgery. I spent university time 90 to 94. Neural network was one of the topics that I have to write papers on. So this is biology. This is linear algebra. Linear algebra, nothing else. And I've seen most of these algorithms. So it's not nuclear science. sometimes things just happening. And regards to algorithm, I think just the backpropagation algorithm, that's probably one that started it. And also the fact that someone from a certain company, 2006, most famous for gaming graphical cards, suddenly looked into parallelism. So sometimes, the avalanche of stuff just works. And that you can see with Ethernet, right? Metcalfe's half duplex has very little in common with the 800 gig Ethernet today. It's not even the same header. However, parallelism is here to stay. And parallelism is a new topic for us. The closest to parallelism in network we have seen is probably multicast. So parallelism has to be able to deal with all networking. That's the sort of the summary of it. Thank you very much.
All right. I think we have a couple of minutes for questions. If anybody wants to have it, and please step a little bit closer to the microphone when you're talking, then we avoid the feedback.
You are between the whole crowd and the lunch now. You know that, right? Sorry.
Hi, Rory. I'm from Crusoe Systems. Sorry to ask you this, but is Ethernet the right tool for the job?
Are you an InfiniBand man or what? Yeah. So, yeah, I'm from Arista, so everyone take this piece of salt. Can you name 2 InfiniBand vendors? There's one, right?
You mean Mellanox and NVIDIA? That's 2.
Let me put it in this way. The best networking card in the industry is the Connect X7 card, but Mellanox card. That's what we do the whole thing on, right? By default, it's InfiniBand. By default, most people swap that to Ethernet. This thing, this Colossus, whatever, it's not built on InfiniBand. There are InfiniBand AI in there, absolutely. But I don't hassle the technology because the Roki header is an InfiniBand header with the Q pairs, right? So that will here to stay. But InfiniBand as a networking piece, just for the sake of it, that there's no competition. It's a layer 2 technology. That's the problem with InfiniBand.
Thank you.
That was very politely said. Usually you InfiniBand guys hack-sack me better than that.